Tristan Erion-Lorico, who is the Vice President Sales and Marketing at PV Evolution Labs. As Tristan is based in Canada and it is very early, we recorded that presentation, but we will have Tristan later on in the panel speaking live. Tristan, the floor is yours.
Hello, everyone. My name is Tristan Erion-Lorico, VP of Sales and Marketing at PV Evolution Labs. Thanks for having me today. I'm excited to be presenting on PVEL's lab results and how they correlate to module field performance, along with some recent testing trends. So my agenda for today will be as follows. First, I'll provide a brief introduction of PVEL. Then we'll have a quick overview of PVEL's product qualification program, or PQP. Then we'll look at about a half dozen examples of where our PQP in-lab results have aligned well to module field failures. I'll then cover some recent trends in our test results, specifically for thermal cycling, damp heat, and PID. And then I'll conclude and briefly discuss our PV module reliability scorecard. So, first things first, a short introduction. For those of you who don't know us, PV Evolution Labs, or PVEL, as we're known in the industry, is the independent lab for the downstream solar market based in California, USA. We're quite well known for our annual scorecard, which I mentioned earlier, the 2022 edition of which has been accessed over 25,000 times since its released last May. Our mission since our founding over 10 years ago is to create the data that matters for solar adoption. As you can see on the screen, we provide a wide range of services to the industry, all of which are focused on advancing our mission. With companies all over the world, including banks, developers, asset owners, insurers, etc., we have over 400 downstream partners in the PV stakeholder community, which we support with data to de-risk their procurements and projects. Also worth mentioning is that in 2021, we became part of the Kiwa Group. As a quick overview of Kiwa, for those unfamiliar, they are a leading global testing, inspection, and certification company headquartered in the Netherlands with over 10,000 employees in a few dozen countries. You can see that they're focused on a wide variety of industries. And for solar, there are multiple businesses offering a wide range of services, including technical advisory, product testing, factory and field inspections, and project engineering. Earlier this year, PI Berlin was acquired by Kiwa, and we are certainly pleased to join forces with them under the Kiwa Group of companies. Okay, now an overview of our product qualification program, or PQP. This will be a refresher on the PQP for those that are familiar with it, or an introduction for those of you who are not. PVEL launched the PQP in 2012 with two goals. One, to provide the necessary due diligence data to the downstream, and two, to provide third-party recognition to module manufacturers who are producing reliable products. One key aspect to the PQP is that the sample modules that get shipped to PVEL are factory witnessed during production. This is a gating step for every PQP we test. Our in-factory auditors follow a multi-step approach to ensure that the bill of materials being used in the modules we receive has been verified and recorded in detail. This is then included in our PQP factory witness reports, and from there can be extracted into BOM exhibits that are provided to the downstream free of charge for use in their procurement contracts. Specifying the exact BOM or BOMs that did well in PQP testing is one of our recommended procurement best practices, and it has huge importance for lab and field correlation, as we'll talk about shortly. Another key principle of the PQP is that it's regularly updated to provide module buyers with consistently relevant data as new technologies and manufacturing techniques are introduced. The current test plan for the PQP is shown on screen there. This was released in October 2021. The updates in the current plan and in all plant PQPs going forward and in the past are really in response to feedback from the market, including conferences like this, feedback from downstream buyers, asset owners, financiers, independent engineers, manufacturers of modules and components, and just industry research. The PQP includes a number of tests designed to address a range of known PV module failure modes, including climate chamber-based tests like thermal cycling and damp heat. It also includes a backsheet test, mechanical stress sequence. You can see our latest addition there is the hail stress sequence. We also look at the module's susceptibility to PID, LID, and LETID, as well as we measure different aspects of the module's performance to aid in energy modeling. A variety of reports are released throughout a PQP's project's duration. And again, these reports are available free to PVEL's downstream partners. So if you're on the downstream module purchasing side of the industry, please contact us to sign up as a downstream partner. All right, now let's get to some examples of lab results closely matching the field. For this first one, we've got two examples of submodule failures. If you're unfamiliar with those, it is when at least a third of the module is removed from the electrical circuit, which can be caused by a short-circuited bypass diode or an open circuit in the module's electrical path, often located in the junction box. On the left side of the screen, we have a module that experienced a short-circuited diode or open circuit in the junction box after 400 thermal cycles in the lab. The module's power dropped by 35%, which we would consider a catastrophic failure. On the right side of the screen, a module we tested from a portfolio of sites in the US had 1/3 of the module not functioning, and we were able to trace this to poor soldering in the junction box. 2% of modules in this portfolio had this particular issue, leading to lost revenue and significant cost increase related to module identification and replacement. It's also likely that other modules in this fleet will fail over time due to the natural thermal cycling that they'll experience while installed. So this gives the site owner very little confidence in their portfolio's performance in the coming years. Another example from our thermal cycling test. Back in 2011, PVEL conducted batch testing, and we found that modules going through thermal cycling showed lots of cell cracks and inactive areas. That can be seen on the left. Our results were ignored by the module purchasers and the developers, and they decided to install the modules anyway. Unfortunately, 5 years later, the site had changed hands and the modules had started failing in the field with hotspots that caused backsheet burns. You can see that burn mark there. The module manufacturer at that time was insolvent, so there was no chance for a warranty claim. And the new owners spent over $400,000 to diagnose and replace the affected modules on their site, which was 2 times their portfolio's annual O&M budget. So a lot of money at stake for something that PVEL predicted in our testing. Switching to damp heat, here's another example from our archives. PVEL tested a BOM of Tier 1 modules and noticed bus bar corrosion and power degradation following damp heat 2000. These were IEC certified modules that had done well during the certification testing's 1,000 hours of damp heat. The developer who installed these started seeing issues with them within a few years. You can see on the right there, visual inspection of the modules revealed evidence of moisture ingress into the laminate, significant signs of corrosion, as can be seen in that image. 100 megawatts of these modules had to be replaced. They were honored under warranty, but the developer had to pay over $10 million to cover the labor cost for module replacement throughout their fleet of sites using these modules. Switching over to our backsheet test, I'm quite sure a number of attendees here are familiar with the issue of cracked backsheets in the field. Building off of the work from DuPont's mass testing, PVEL's backsheet durability sequence has been shown to reveal backsheet polymers that are prone to cracking. You see an example of that on the left, and on the right is a module with similar cracks from the field. Thankfully, in our BDS testing on modules in the past 3 years, we have not seen backsheets that were susceptible to cracking. So hopefully that's a sign of the industry learning lessons and overcoming past issues. But there are many backsheet varieties on the market, and PVEL has only tested a relatively small portion of them, so it's possible that some commercially available backsheets are still at risk of cracking after long-term exposure in the field. Okay, now switching to our mechanical stress sequence. This combines static mechanical loading, dynamic mechanical loading, thermal cycling, and humidity freeze. And we've seen a number of catastrophic failures while doing this test, mostly related to glass breakage. This is quite surprising, actually, as we do the test using the traditionally most conservative mounting, with rails running perpendicular under the long frames, about a quarter of the module's length from either end. We're also only applying the IEC 61215 certification test minimum static load pressure of 2,400 pascals. In this particular example on the left, the frame sealant failed, leading to the glass being ripped out of the framing channel and then the glass breaking. On the right is an image from a report on module performance following Hurricane Irma and Maria in the Caribbean. The red arrows, point to 2 modules where the laminates became liberated from the frames. The laminates are gone. And that's similar to what we saw in the failure mode on the left-hand side in the lab. And for this last example, comparing results from our in-lab hail testing versus a fielded module, the fielded module, we go to sites after hail and we image the modules to see which are bad and which modules have micro cracks basically and which don't. You can see that the crack patterns in the tested module from the lab on the left is very similar to the one on the right. On the left, we used 50-millimeter freezer ice balls, and on the right, of course, is from naturally occurring hail. Okay, so now switching topics a bit, I'd like to look at some recent trends in our testing, starting with thermal cycling. In this case, we're looking at just the multi-bus bar results for thermal cycling from 2016 to 2021. Thermal cycling is a test where the module cycles from -40 degrees up to +85, back down to -40. It does that 600 times. The IEC certification requirement is only 200 cycles, but for the PQP, we triple that. And this test is known to identify soldering-related issues. You can see that a few years ago, the results ranged quite a bit. There was good multi-bus bar bomb in 2017, but by 2016, or earlier in 2016, the results showed areas for improvement, similar with 2019 and even into 2020 with that outlier there. By 2021, though, the results for multi-bus bar thermal cycling were quite good. We've got quite a tight range, and the results are higher than in previous years. This shows that the technology progressed, and as it became more common throughout the industry, the reliability improved. So certainly a good news story for the industry here. Here's a specific example of that. Both these modules are from the same manufacturer. On the left is their module from 2016. It has almost 10% degradation and clearly lots of soldering issues shown in that EL image. On the right is their module from 2021. They've addressed those soldering problems, and the module here is considered a top performer. So definitely a good news there. And you can see that, as the technology is deployed, the reliability in this case got better. Moving on to a recent trend in our damp heat testing. Damp heat, here we have 2,000 hours at 85 degrees and 85% relative humidity. The IEC certification requirement is only 1,000 hours. This test finishes with a 48-hour stabilization run that reverses any boron oxygen or BO destabilization effects. This test is known to reveal corrosion and or delamination in susceptible modules, as we saw in my previous example. For the last few years, as PERC modules have dominated our test population, and most of the degradation we saw was related to boron-oxygen destabilization. More recently, we're seeing relatively high levels of damp heat-related degradation that does not recover following that stabilization. In fact, in 2021, we were seeing some of the worst damp heat results in PVEL's history. We don't know yet if this is related to the switch from boron to gallium, a change in the metallization, or something else. You know, research is ongoing to figure out what's happening here. In the meantime, here's an example. This is from one manufacturer in 2018. You can see that they experienced boron-oxygen destabilization after damp heat 2000 with that 8% degradation. But after the stabilization, basically all of that is erased. And the module almost looks brand new in the EL image. Here's a more recent example, though, from the same manufacturer, where there is no longer boron-oxygen destabilization effects, and therefore no recovery during that stabilization, but instead there's a far more traditional damp heat failure mode, where you can see the corrosion that kicks in starting at damp heat 2000 and extends throughout the rest of the test. And there's very little recovery in the stabilization step. So this is truly a damp heat related degradation. Okay, last example, I want to look at potential induced degradation. I imagine most of the participants are familiar with PID. For those that are not, this is a phenomenon that causes degradation at high voltage, and it's accelerated via high heat and high humidity. For our test, we subject the module to damp heat conditions while applying the maximum system voltage between the cells and the frames. This lasts for 192 hours, while the IEC certification requirement is half of that. On the screen, you can see all of our PID negative polarity results between 2014 and 2021. The median results are relatively stable over that time, but there are lots of outliers which cause the average to be lower in previous years than what we've seen for the past 4 years. I wanted to parse that data to only look at PERC PID results, and now that's what's on screen here. So I've separated that by glass backsheet bombs on the left and glass bombs on the right. There's obviously more outliers on the glass bombs than on the glass backsheet bombs. So let's have a look at those, you know, -8 to -10% degradation outliers. And that's here on this slide, where it's just those glass bombs, and we've separated them by the type of rear encapsulant that was used, whether that rear encapsulant is POE or EVA. You can see in 2020 and 2021, there's really a bifurcation between glass using POE on the rear side and those using EVA. Most manufacturers we work with do use POE, and those clearly perform quite well. For manufacturers using EVA on the rear side of their modules have much worse results. You can see that there's quite a difference there. Perhaps some good news is that those results may recover in the field, or may not. You know, that PID might not be field relevant. Here's an example of one of those glass modules using rear side EVA, and you can see that much of the PID recovers after a short 2 kilowatt-hours per meter square UV exposure. It's not yet clear, though, how field relevant the PID degradation or the recovery is. I'm aware of some module purchasers as well as manufacturers concerned by this and not knowing, is there a real PID risk here or not? And to solve that, they're sticking with using POE in their glass modules. So that's basically it, other than a brief conclusion here. I know we went through a lot of data. I've shown many examples of how PVEL PQP test results can predict fielded module reliability. As you know, there are a significant number of variables in module design and high volume manufacturing. As technology changes, reliability risks are increased. Based on my thermal cycling example, it's clear that this reliability risk can dissipate over time, as we saw with multi-busbar modules. But that's not always the case, as we've seen in the Stampede trend on perk modules, getting worse over time. So we can confidently say, based on PVEL's over 10 years of test data, that not all modules are created equal. We're here to help determine which modules are reliable and which are not. And that's really PVEL's main focus in the industry. And one way we do that is via the PV module reliability scorecard. As I said earlier, we released the 2022 edition earlier this year. It's been accessed by over 25,000 unique website visitors located in over 100 countries. It's got lots of great insights into our test results and their meaning for the industry, as well as highlighting 25 different module manufacturers that have produced 122 different top performing model types. For the first time, we also included a searchable database of the top performers. You can filter on cell technology, cell size, factory location, PQP test, etc. If you want to learn more, I encourage all of you to check out modulescorecard.pvel.com. So I thank you for your attention. That concludes my presentation, and I look forward to the panel discussion at the end of today's event. In the meantime, if you have any questions or you would like to get in touch, please contact us at pvel.com or via my email address on the screen. Thanks very much.
Thanks, Tristan.